students. Welcome to Nuclear Physics lecture. I'm Dr. Fawaz Ahmed. In this lecture, we will discuss about some of the shortcoming and semi-empirical mass formula or an liquid drop model. So let's start our discussions with the shortcoming and semi-empirical mass formula. So the first shortcoming that we will discuss about, the problem with the magic number and binding energy for nucleon. So just like you can see it here for yourself that we have a graph by having a clear look at this particular graph in which the binding energy for nucleon is plotted against the nucleons. So here you can see it by yourself. We have magic numbers, that is equal number of neutrons and protons. That represents particular magic number, but in spite of that you can see that that semi-empirical mass formula does not apply for the atomic mass greater than 20. So this is one of the shortcoming of the semi-empirical mass formula. Another drawback of the semi-empirical mass formula is that there are systematic deviations from semi-empirical mass formula for the atomic mass greater than 20. So again, if you have a close look at this image, at this diagram, so you can see it here for yourself that how the deviations, that how the deviations occur from semi-empirical mass formula. We last time we have discussed the binding energy for nucleons. We discussed the curve in detail in last lecture. So if you remember there, so we said that the binding energy for nucleon curve is systematically it increases. In real curve, so it's increased for until we reach the iron mountain. So up to the iron mountain, so we have discussed last time that then the curve systematically to a certain value it decreases and then it becomes stable and reach to a particular value to uranium 235. But here you can see that unlike that particular curve, if we apply the binding energy, the sample empirical mass formula, so we get the systematic deviations. It's the deviations from for the atomic number greater than 20. So this is against a shortcoming of the semi-empirical mass formula. Another shortcoming, another disadvantage of semi-empirical mass formula is that in magic number and separations energy, that is neutron separations energy. And here we take the example of the barium. So last time we took two isomers and we discussed that how those isomers after beta decay they come toward the bariums. We took the example of smaller atomic mass number and then the bigger atomic mass number, and we have discussed how they come toward the stability. They come toward the barium. So by considering barium neutron separation energy in mega electron volt, it can easily be observed from this diagram that neutron separation energy, we saw here, we saw truth from pairing term. Whenever we have the pairing term, so just like you can see it here in this particular diagram, we observe truth from pairing term, and here you can see it here. Atomic number, the magic number 82. Here you can see that we have a step down when a neutron goes across a magic number at 82. So again, this is this is something against the semi-empirical mass formula. And if we look at the abundance of the element in the solar system, so we might observe that here again we have something which is against the semi-empirical mass formula. Or semi-empirical mass formula is not able to explain the abundance of the elements in the solar system. So here you can see it, or you can observe the thing that's how it's been plotted. that is the abundancy number related to silicon s 10 raised to the power minus x plotted against the atomic mass number. So here you can see that means again we have a drop at the magic number 82. It's a magic number 82 for the photons, and magic number 126 for the neutrons. And here you can observe it that whenever we have magic number 82 for the neutron, so we get again the tooth-like structure here. That's been rising, that we already discussed on the previous slide. And we have the iron mountains, just like you can see it here. But this iron mountain is smaller than the oxygen that's been providing a burning sensation. So again, this is something that is against the semi-empirical mass formula. uh, Other evidence for the magic number, that is if we consider the case of isomer. So nuclei with the neutrons magic number have abnormally small neutron capture cross sections, uh, and close to the magic number nuclei can have long life excited state, that is 10 raised to power minus 6, called isomers. So one peak of the island of the isomerism, that you can see it here in this particular diagram. So they show up a nuclei with large energies for their first excited state. That is, a nucleon has to jump across a shell closure. So again, it's a drawback of the semi-empirical mass formula. So other shortcomings of semi-empirical mass formula include spin and parity of the nuclei do not fit into a drop model. uh, Magnetic moments of the nuclei are incompatible with the drop. So actual value of the nuclear density is unpredicted. Value of the semi-empirical mass formula coefficient except Coulomb and asymmetry are completely empirical. So all these shortcomings, they led towards a nuclear shell model. That is, we have a question in mind. And what were those questions? So the first questions which arises by having a close look on the shortcoming and the liquid drop models. The people asking the question that how to get to a quantum mechanical model of the nucleus. um, can't just solve the neutron body problems because we don't know if a two body model makes sense. Means it does not make much sense for a normal liquid drop. uh, if it did make sense, we don't know the two body potentials yet, and if we did, we could not even solve a three body problems, but we can solve a two body problem. So need simplifying assumption. So these were the questions which lead us towards another models that we call the shell model. So in next lectures we will have detailed discussions about the shell model. So till then, bye bye.